In 1994, Andrew Wiles solved a mystery that had stumped mathematicians for 357 years. The 17th century French mathematician Pierre de Fermat states that you can't find numbers where x to the n plus y to the n is equal to z to the n when n is a whole number greater than 2. For example, 3 to the power of 3 plus 4 to the power of 3 equals 91, which is not the cube of any whole number. Fermat claims to have proved his theorem, writing in his copy of Arithmetica, an ancient Greek text on number theory. I have discovered a truly marvelous proof of this, which this margin is too narrow to contain. Unfortunately, he never wrote down his proof, not anywhere that anyone has ever found. For over 300 years, mathematicians puzzled over this perplexing problem, which is similar to the Pythagorean theorem, but applies to exponents greater than 2. Andrew Wiles was a young boy when he stumbled upon Fermat's last theorem at a library in Cambridge, England in 1963. As he recalled in an interview later featured in the book Fermat's Enigma by Simon Singh, which I highly recommend, here was a problem that I, a 10-year-old, could understand, and I knew from that moment that I would never let it go. I had to solve it. His determination was extraordinary, considering the brightest minds in math had failed to crack it for centuries. The 18th century Swiss mathematician Leonhard Euler proved a specific case where there are no solutions for n equals 3, but his work didn't extend to other exponents. Euler even asked a friend to search Fermat's house just in case he had scribbled down his proof somewhere, with no luck. The wealthy German industrialist Paul Wolfskehl was so miserable because the woman he loved didn't love him back that he planned to end his life, only to be reinvigorated by Fermat's puzzle. He never solved it himself, but he offered a reward of 100,000 German marks to anyone who could, motivating the next generation of mathematicians. When Andrew Wiles was a grad student at the University of Cambridge in the 1970s, his supervisor John Coates suggested he study elliptic curves, which proved crucial for solving Fermat's last theorem. In the 1950s, Japanese mathematicians Yutaka Taniyama and Goro Shimura suggested that for every elliptic curve, there is a corresponding modular form. The Taniyama-Shimura conjecture connected two distinct areas of mathematics. Later, Ken Ribet, a professor at UC Berkeley, linked their conjecture to Fermat's last theorem. How? He showed that if Fermat's last theorem were false, certain elliptical curves would have to exist. However, the Taniyama-Shimura conjecture implied that those curves could not exist. Therefore, if the Taniyama-Shimura conjecture were true, Fermat's last theorem would also be true. Proving the conjecture would prove Fermat's last theorem. The problem was Taniyama and Shimura never proved their own conjecture. Tragically, Taniyama committed suicide in 1958, leaving a note that read, "I am in the frame of mind that I lost confidence in my future." His fiancée took her own life shortly after, writing, "We promised each other that no matter where we went, we would never be separated. Now that he is gone, I must go too, in order to join him." In 1986, Andrew Wiles was sipping iced tea at a friend's house when his friend mentioned Ken Ribet had proved the link between Taniyama-Shimura and Fermat's last theorem. Andrew recalled, "I was electrified. I knew that moment that the course of my life was changing, because this meant that to prove Fermat's last theorem, all I had to do was prove the Taniyama-Shimura conjecture. It meant that my childhood dream was now a respectable thing to work on. I just knew that I could never let that go." By this time, Andrew had moved to the US, where he was a mathematics professor at Princeton University. When he wasn't lecturing, he was in his attic office trying to prove that every single elliptic equation could be correlated with the modular form. Only his wife knew what he was up to. He kept his work a secret, not wanting to be distracted, though there may have been another reason for his secrecy. He may have feared that if his progress leaked, a rival mathematician might beat him to the punch and claim the glory. He cleverly threw his colleagues off his track by publishing his ongoing research on elliptic equations every 6 months, making it seem like he was keeping busy while actually devoting his time to the age-old enigma. He began by proving the connection for a specific class of elliptic curves, like knocking down the first domino in a long line. The challenge was to ensure that if one domino fell, it would topple the next. Andrew had to show that if one element of the elliptic curve series matched the corresponding element in the modular form series, then the next elements would also match. Yet he struggled to topple the rest of the dominoes. 5 years after working in secret, he decided to emerge from his hermit-like state in hopes of finding new ideas. In 1991, he attended a major math conference in Boston where his PhD supervisor, John Coates, mentioned that a student of his, Matthias Flack, was working on a powerful way of analyzing elliptic equations, building on the work of Russian mathematician Viktor Kolyvagin. Andrew realized this Kolyvagin-Flack method could help him topple the rest of the dominoes, ultimately proving every elliptic equation could be matched to a modular form. But this involved incredibly hard mathematics and took several more years. After 7 years of working all by himself, he finally decided he needed some help. In 1993, he confided in his colleague at Princeton, mathematician Nick Katz. They arranged a secret weekly meeting disguised as a graduate course, where Nick meticulously checked and verified Andrew's calculations and assessed that the Kolyvagin-Flack method worked perfectly. There was still one missing piece of the puzzle. Andrew used a key insight gleaned from a paper by American mathematician Barry Mazur to complete the puzzle in May 1993. It was time to tell the world he had solved the world's hardest math problem. He chose to do so at a conference at the Isaac Newton Institute in June 1993 in his hometown of Cambridge. An air of excitement filled the room as rumors spread of his breakthrough on the more than 300-year-old mystery. Andrew recalled, "There was a typical dignified silence while I read out the proof, and then I just wrote up the statement of Fermat's last theorem. I said, I think I'll stop here." And then there was sustained applause. Mathematicians usually don't make headlines, but this was an exception. The excitement was palpable, yet the proofs still needed to be verified. He submitted his draft to the journal Invenciones Mathematica, where the editor, Barry Mazur, selected 6 referees to pore over Andrew's 200-page work. This was subject matter that perhaps only a half-dozen people in the world could fully grasp, as John Lynch, editor of the award-winning documentary Fermat's Last Theorem, put it. During this rigorous scrutiny, a flaw emerged. One of the referees, Andrew's Princeton colleague Nick Katz, discovered a gap in the part of the argument involving the Kolyvagin-Flack method. Nick and Andrew had missed this during their earlier secret meetings disguised as lectures. Was Andrew's proof about to collapse like a house of cards? Despite the setback, he remained optimistic. He was confident that Kolyvagin-Flack just needed a little tweaking. He retreated to his attic once again, but it was slow going. His wife Nada had told him she wanted everything corrected by her birthday on October 6, 2 weeks away. But as time went on, with no manuscript published, rumors began circulating that there were issues with his proof. Andrew had no choice but to address the speculation publicly in a forum at the end of 1993. During the review process, a number of problems emerged, most of which have been resolved, but one in particular I have not yet settled. I believe that I will be able to finish this in the near future using the ideas explained in my Cambridge lectures. Winter passed, and he was still nowhere close to completing the proof. He decided to bounce ideas off of someone he trusted. His former student, Richard Taylor, now a Cambridge lecturer and one of the referees who looked over his proof. They worked through the summer of 1994 without any progress. Andrew was at wit's end and thought of giving up. But Richard persuaded him to keep working on until Richard returned to Cambridge in September. That extra month made all the difference. The morning of Monday, September 19, 1994, Andrew was again intensely examining the Kolyvagin-Flack method, trying desperately to understand why it didn't work. Suddenly, he had an incredible revelation. Although the Kolyvagin-Flack method wasn't entirely successful, it provided enough insight to revive his original approach using Iwasawa theory, a theory of analyzing elliptic equations that he had learned as a student at Cambridge. Combining the two methods, which were inadequate on their own, provided the eureka moment.
It was the most important moment of my working life. Nothing I ever do again will. Sorry.
After 8 years of dedicating himself to one task, Andrew's 129-page proof was published in May 1995, putting to rest the greatest mystery in math. He reflected, Having solved this problem, there's certainly a sense of loss, but at the same time, there is this tremendous sense of freedom. That particular odyssey is now over. My mind is at rest. If you've been inspired by Andrew's remarkable achievement and want to improve your math skills and, who knows, solve the next big mathematical mystery, Brilliant is the perfect place to start. If you've ever felt that math is hard, Brilliant is a website and app that makes math easy and intuitive. In their measurement course, you'll learn to find angles, side lengths, and areas by recognizing relationships between shapes. No heavy calculations are needed. Brilliant's vector courses will enhance your ability to visualize and solve complex problems in multi-dimensional spaces. Brilliant has something for everyone. If you're interested in coding, you can get familiar with Python and start building programs on day one with a built-in drag-and-drop editor. You can try Brilliant for free for 30 days by signing up with my custom link in the description, brilliant.org/newsthink, or scan the QR code on your screen. By signing up with my link or code, you'll also get 20% off your annual premium subscription, giving you access to thousands of courses. Thanks for watching. For Newsthink, I'm Cindy Palm.